die will not Okay, welcome everybody to this term's Strachey Lecture. So this is our distinguished termly lecture, which is named for Christopher Strachey, who founded the programming research group here and was one of the leading figures in the early history of computing. Before I introduce our amazing speaker, I want to thank our sponsors, Oxford Asset Management, who have been generously supporting this series since 2015. And they enabled us to bring great people here. I think some of you have donuts and things. If any researchers and students want to meet them afterwards, please do that. Okay, so it's a great pleasure to introduce Christel Baier. Christel is super well known for her work in verification. And actually, Christel's also very modest because the biography she gave me omitted all sorts of things, but luckily for me, I used Google and discovered them for myself. So I discovered, for example, that her textbook, The Principles of Model Checking, has been cited more than 8,000 times and is essentially the book in model checking. And she also has some very, very influential papers, including a work called Model Checking Algorithms for Continuous Time Markov Chains, which again has really very, very many citations and introduces both the new logic and new model checking algorithms. Christel is the author of the verification column in ACM Siglog News and has a bunch of honors, including Academia Europa and an honorary doctorate from RWTH Aachen. And she's really active in supporting German computer science. So I found Christel on just about every German computer science committee that exists. She's here today talking to us. The title of the talk is From Classical to Non-Classical Stochastic Shortest Path. And welcome, Christel. And I'll put this lower, yes. Do you like that? Yeah.
Thank you. Does the mic work?
It does.
It does, okay. Yes, thank you very much for inviting me. Thank you very much for organizing this event. Thank you very much for the sponsoring here. It's a great honor for me to give this presentation. Well, I chose here a topic which has a long history. So indeed, first research was done 60 years ago. But in the end, for these non-classical versions of the shortest path problem, then it's more recent work. And before starting with the technical things, I would also like to say it is almost 30 years ago that I visited Marta Kwiatkowska in Birmingham. We just were thinking which year it was, 95 or 96. And this was for me the first time to get in touch with questions concerning the verification of probabilistic programs or probabilistic systems. And at this time, I also read these old papers about the classical stochastic shortest path problem, and I would have never thought that 30 years later I will give a talk about this topic. So I would have expected that all the problems have been solved. Yeah. So what is the question of the classical shortest path problem? So more or less the task is to construct a strategy or policy for traversing a graph with probabilities attached, such that the expected accumulated costs until reaching a target is minimal. So the main problem is to minimize the expected costs or weights. Well, for motivation, so this is a map. Here is Dresden, where I live. Here is Oxford. And going from Dresden to Oxford, well, there are many possibilities. Taking a car, taking a train, taking a flight. Then there are no direct flights. This is an extremely small airport that we have in Dresden. Then I have to change in Frankfurt or in Munich or in Berlin or whatever. And there are a lot of decisions that have to be made. And there's a lot of uncertainty. So the flight might be delayed, or the flight might be cancelled, which is indeed the case. So my backward flight has been cancelled. And so finding one way, shortest in the sense of shortest time for me in expectation. So this is one instance of the shortest path problem. Now, indeed, in different communities, AI, planning, robotics, operations, research, this is a very classical and fundamental problem, but also for the verification of randomized systems or distributed randomized algorithms. Then, for instance, one might ask, what is the, in expectation, the time to termination, the maximal or minimal time for termination, or expected costs, the maximal cost that can happen in the worst case. Now, the formalization of, the formalization of these problems is using Markov decision processes. Now, I do not want to bother you with complicated definitions, which is not that complicated in that case. The simplest way to explain them, at least I find, is to do the following. We start with a classical transition system, here shown on the left, where in every state there is a choice between different actions. And in this context, we consider the choice of different actions as a non-deterministic choice. So different than for finite automaton, where we expect to have the same label for a non-deterministic choice. Here, the choice between alpha and beta is considered to be non-deterministic. The other extreme is a Markov chain, where we do not have non-determinism at all. Instead, for every state, we have a distribution for the successor states. And a Markov decision process is somehow the mixture of both. So for every state, we have a set of action. And for each action, we have a distribution for the successor states. This is missing because of this one. Maybe. Yeah, so for alpha, we have the distribution 1/4, 3/4, and likewise, we have here a distribution for the beta. And now in state S, the choice between the different actions is considered to be a non-deterministic one. And having chosen the action in a state, then we have a probabilistic choice, which is viewed to be an internal decision, which is indeed the successor. Now, to talk about probabilities or expectations in Markov decision processes, we need some instance which resolves the non-determinism. And this is what we call schedulers or policies or strategies. So they take the history, what has happened, so the sequence of states and actions that have been taken in the past. And then for the current state, they choose one of the actions, possibly in a randomized way. And doing this, then you can, given such a scheduler, you can unfold the behavior under that scheduler into a tree-like Markov chain, and there we have the full machinery to reason about probabilities, expectations. If you are not familiar with that, just use your intuition. I think this would be enough for this talk. And for the shortest path problem, we deal with weights, integer weights that are attached to the state action pairs. So now here is the definition. The only important thing is that throughout this talk, when I say an MDP, I always mean a finite state MDP. So we only have finitely many states and finitely many actions. Now, and a scheduler can be formalized as a partial or as a function from finite paths to distributions over actions. This would be the randomized case. And the deterministic case is where these distributions are Dirac distributions, which means that a single action is chosen as probability 1 or is chosen deterministically, a unique action. And another important notion is that of a memoryless scheduler. They do not look for the full history, they just look for the current state. And whenever I visit the same state multiple times, I make the same decision. This is meant by memoryless. And on the following slides, I often use the short form notations MD for memoryless deterministic and MR for memoryless randomized. And another important concept that has been introduced by Luca de Alfaro more than 20 years ago is the notion of an end component, which, to say it in easy words, is a strongly connected sub-MDP. And by saying sub-MDP, what we do is the following. for every state, we have a set of actions that can be taken, and now we take just a subset of these actions. And this gives you a sub-MDP. The probabilistic choices for these selected actions remain the same. They remain unchanged. So if you look for the underlying graph, then it's indeed a subgraph. And for this being an end component, then this graph needs to be strongly connected. And there is one theorem that has been established by Luca de Alfaro in his thesis 97 and also in multiple papers, what I called here the fundamental property, which is somehow the MDP analog to this fact that in a finite state Markov chains, we know that almost surely, so with probability 1, a bottom strongly connected component will be reached and the system will stay there forever. And the MDP analog uses these end components. It states that no matter which scheduler you choose, then the limit of almost all infinite passes will constitute an end component. And here by the limit, the meaning is we look for the state action pairs that occur infinitely often. Now, here's an example. Here we have an MDP and we have, oops. It stopped working. Does it work here? Yeah. We have two end components. Does this still work? Yeah. We have here two end components, and we have this state here. Oh, that's great. But this one, for what? This one here is a trap state, so a terminal state where no action can be taken. And then Alfaro's lemma applied to such MDPs that might have such trap states means that under each scheduler, almost all maximal passes, so either finite passes that end in a trap or the infinite ones, they indeed end either in a trap or they eventually realize an end component. And by realizing an end component, I mean that the state action pairs that occur infinitely often constitute an end component. And for the special case where we do not have, did it work? Okay, where we do not have end components at all, so an EC-free MDP, then Alfaro's lemma simply states that with probability 1, no matter which scheduler we choose, the system will end in a trap state. So now the typical task are synthesis problems for MDPs, or formalized as synthesis problems would be, given such a finite state MDP, find a scheduler that maximizes or minimizes the expectation of some random variable. So, and the input of this random variable are simply maximal passes. So one very popular measure is the discounted weight. Remind that we have these integer weights for the state action pairs. And now this discounted weight of a maximal path, we take the sum over all positions in that path. We take the weight which is collected for the corresponding state action pair, Si alpha I, and we multiply with the i's power for discount factor gamma. And this gamma is some value strictly between 0 and 1. And now with gamma being strictly between 0 and 1, then we do not have convergence problems, even if this sum is infinite. Total weights is more or less the same, but you can think of it with discount factor 1 or without any discount factor. Now, here indeed, convergence is an issue for infinite passes, and I would say it is not that interesting with the total weight for infinite passes without any further side constraint. What has been done in the literature is either to consider here only finite passes, either in a finite horizon setting, which means that we have some fixed bound for the length of the passes that we consider, and then we look for the maximal expectation after exactly n steps, or the infinite horizon case, where we have a distinguished goal state, and we only accumulate the weight until we reach this goal state. And with a side assumption that we only look for those schedulers that indeed reach this goal state with probability 1. These are the so-called proper schedulers. And there is another very prominent measure or random variable which is used in the literature. This is the mean payoff or the long run average. So what we do is we take the partial sums of these total weights. So we look for all the prefixes, the finite prefixes of a given path, and we take the average for these finite prefixes. This is this value here. And then we either take the lim_inf or the lim_sup for these values. Now, given a single path, then the lim_inf and the lim_sup, they can be different values. However, what is known is that in finite Markov chains, that it makes no difference whether we deal with the lim_inf or the lim_sup in expectation. These are the same, and this result carries over to Markov decision processes where the maximum doesn't change whether we take the lim_inf or lim_sup, and same for the minimum over all schedulers. Well, and moreover, and I will not zoom into the details, there are efficient algorithms to compute a memoryless deterministic scheduler where the max or the minimum are achieved, and these can be computed using linear programming techniques. So now let's go more into the direction of the shortest path problem, and let's look first for the discounted case. And here the key concept are the so-called Bellman equations. So this it was somewhere in the 50s, so quite a long time ago, when he introduced these Bellman equations. So now we are in the discounted case. So the task is to find a scheduler that, say, maximizes the expected discounted weight. And here we go. Here are the Bellman equations. So the idea is to characterize the global maximum by local maxima in every state. So S is a state, and XS is a variable for the maximal expected discounted weight that we can achieve from state S. So if we treat state S as an initial state. And then this value XS equals the maximum over all the actions that can be taken in state S. And for each such action, we look for the weight of the state action pair S alpha plus the weighted sum of these values for the successors. And here the weights are given by the discount factor gamma multiplied with the transition probability going from S when taking alpha to state T. And this is a recursive equation. So XS equals something, and here on the right-hand side, we have values xt for the successors. So you can think of it as a function that maps vectors with one component for each state to vectors. And what has been shown is that this function, thanks to this discount factor gamma, is a contracting map on a Banach space, so it has a unique fixed point. And this indeed also is the key property to establish algorithms. So one of them is derived linear programming techniques, namely, instead of saying here XS equals the maximum, we say XS is greater or equal than all these values for each action that can be taken in state S. And to ensure that we have XS equals the maximum, we minimize all these values. So this is one thing, and the other thing is what can also be derived from this is the value iteration. So we just so this function f, we start with an arbitrary value or 0 in every component, and then we simply successively imply this function f, and convergence is guaranteed. And there is also a technique I will not speak about, which is called policy iteration. So we successively improve a memoryless deterministic scheduler, and eventually this stabilizes in an optimal solution. So now this was the case, this one here, for discounting. And remind, for total reward, I said this is essentially the same, but without this discount factor. And indeed, the Bellman equation itself, they are still, for this infinite horizon case, they still look like this, unless state S is already one of these distinguished goal states. In this case, the XS is simply 0. But otherwise, we indeed have the same equation, and here was the discount factor gamma, which is 1 or can be dropped. But now things are more difficult. This before, I said we have a contracting map, but this is not clear here, not in all the cases. We don't have this discount factor anymore. So this needs additional things to make sure that we have a unique fixed point and so on. And all this was, let's say, here we talk about the stochastic shortest path problem, and all this research is about these extra things that we need. So just I skipped the outline at the beginning, but now here comes. So what I just did was to give you some basics about the model we talk about and these important measures. And now we talk about the stochastic shortest path problem, first the classical one, and then later on variance. So this notion, stochastic shortest path problem, and the main results, they go back to Bertsekas and Zitslikis from the year, this is very small, it is 91, in a paper published in Mathematics of Operations Research. And in this paper, they have a very nice section on the related work, or the summary of the work that has been done at this time, so a summary of the state of the art. So here is this paper from 91, and it goes back to 62, where this problem has been investigated first. And they also nicely describe, they even apologize to introduce a new name for this, because this was used under different names, under three other different names before. But they also explain that this is in the style of classical shortest path problems, which are known from graph theory. So now let's look for this picture here. We have a weighted finite state Markov decision process, and we have a certain goal state, which is the target state that we want to reach, and we accumulate the weights until we reach this goal state. And then we want to reason about the min or maximal expectation for this random variable. Now, for the rest of the talk, I will consider the stochastic longest path problem, where we have here the maximum. The techniques for minimum are completely analogous. So the first result, and this goes back to the late 60s, was that in the special case where under every scheduler, so the minimal probability to reach the goal state is 1. In this case, what has been proven is that the Bellman equations, they still work, and they yield a contracting map. So MDPs of this form are also called contracting MDPs, and these are exactly the EC-free, those that do not have end components. And it was shown that there is a reduction to the discounted case in this case. So all this machinery for discounted weights works also for this case. Now, the contribution of Bertsekas and Zitslikis was, okay, this requiring that under every scheduler we reach a goal state is a very strong requirement. Now, let's relax it by considering only those schedulers, what they call the proper schedulers, namely those that reach the goal with probability 1, but there might be others. So, and they also achieved that under certain conditions, we can still rely on these Bellman equations and these techniques that have been developed for the discounted case, but they needed a second condition here, which is that, that the total expected total weight under each improper scheduler. So each scheduler that does not reach the goal state with probability 1 must be minus infinity. And they showed that if these two conditions hold, then the maximum is indeed finite, and all this machinery that has been developed for the discounted case still works. So now the question is how to check this condition, this second condition. The first one, this is simple. There are graph algorithms to do this in polynomial time. But how to check this condition, the second one? And the next thing is, so if these two conditions hold, then the maximal expectation is finite, but there can be other cases where the maximal expectation is finite. So it's not a complete criterion. So what to do in these cases where it is finite, how to check this, and how to compute in these cases an optimal scheduler and the optimal value. And the first answer was given to these questions was given by Luca de Alfaro in his Conca 99 paper, where he considered Markov decision processes where the weights have all the same polarity. Either they are all non-positive or they are all non-negative. And what he did was he provided a transformation to the case of Bertsekas and Tsitzlikis, so that these two conditions hold for a transformed MDP. And the idea here for the case, this is now for the case where all weights are non-positive, so either negative or 0, then he observed the following. Whenever you have an end component where every state action pair has weight 0, then you can collapse them to a single state. Then it's no longer an end component. And in that way, you can remove all these end components consisting of what I call here 0 end components. And what remains is an MDP where each end component contains at least one state action pair with negative weight. And the other weights are non-negative, non-positive anyway, which gives you that the expected value of the total weight is indeed minus infinity for each improper scheduler. And in the case where all the weights are non-negative, then Alfaro proved the following. The maximal expectation is finite, if and only if the weights in all end components are 0. So no end component contains a state action pair with positive weight. And in that case, one can do the same thing. One collapses all these 0 end components, and the result is an MDP that has no improper scheduler at all. They're all the remaining, so the end, if all these end components enjoy this, then after this collapsing the 0 end components, there are no end components anymore. And these concepts can also be generalized for the case of arbitrary integer weights. So we can have a mixture between positive and negative weights. And let's have quickly a closer look in this criterion for finiteness and for this transformation. There is some cleaning up to make sure that from every state we can reach the goal state with probability 1, and that non-reachable states are removed and so on. I will skip this. Then after such a cleaning up, the result or characterization of the finiteness looks like this. The maximal expectation is finite if and only if the MDP has no weight divergent end component. And an end component is said to be weight divergent if it has a scheduler such that for almost all the passes along this scheduler, the lim sub of these prefixes of the weights tends to infinity. Now this observation then yields an algorithm for checking finiteness, compute the maximal end components. This can be done with an iterative, strongly connected component computation in quadratic time. And then one can check this weight divergence separately. To give you an idea for that, let's have a closer look. So this was again the definition of weight divergent end components. They exist a scheduler such that almost surely the sim loop tends to plus infinity. One special case are so-called pumping end components, where the same thing holds, but now in a stronger form, namely even the lim inf goes to plus infinity. This, for instance, applies to an end component, which is here just a Markov chain, which is completely uniform. So S and T, just with uniform probability, we stay in that state or go to the other state. And for one state, we have the weight +2, and for the other one, -1. Then, if you look for the accumulated weight, almost surely it goes up and up and up and higher and higher and higher, such that indeed the lim inf will be plus infinity. Another extreme situation is what has been called gambling end component. Here, the lim inf goes to -infinity and the lim sub goes to plus infinity. So we still have this weight divergence condition here on the right-hand side. So, and this would be the case where this accumulated weight oscillates. So it goes down and higher and down, so up and down and up and down and so on. So, and now here comes an algorithm to check weight divergence, assuming that we have a strongly connected Markov decision process. And this assumption is justified because, as I said before, to check this finiteness of the maximal expectation, it suffices to analyze the maximal end components separately. So we are in this strongly connected case. So we first compute the maximal mean pair-off and a corresponding memoryless deterministic scheduler. If this mean pair-off is positive, then we can safely return yes, because just remember the mean pair-off was defined as the average of the weights that we collect in the first n steps, and then the n goes to infinity. So if this is the case, if even this mean pair-off is positive, then we are in a pumping case. If the mean pair-off of this scheduler, or the maximal mean pair-off is negative, then we can safely return no, this is not the case. It cannot be weight divergent because the maximal expected mean pair-off in all end components must be negative. So when we arrive here at item 4, then neither 2 nor 3 applies. So which means that the expected mean pair-off or the maximal mean pair-off is 0. Now this scheduler sigma is a memoryless deterministic scheduler. It induces a Markov chain. Now this Markov chain, you can consider it as a graph. It has certain strongly connected components, and now look for those that are at the bottom that cannot be left. Pick one of them. So if this one is gambling, and remind this means that the lim sub goes to plus infinity, the lim inf to minus infinity, then we can safely return yes, because gambling implies weight divergence. The question is how to check this being gambling or not. This is an NP-hard problem in general, but here we are in a simple case. We have a Markov chain, so this E is indeed a Markov chain, and we know that the mean pair-off is 0. But then being gambling is equivalent to the existence of cycles where the accumulated weight is positive, which again is equivalent to the statement that there are cycles where the accumulated weight is negative. So, and this is a simple graph condition. So this can be also checked just by graph algorithms. Now, what remains to consider is the case that this E is not gambling. But then the only thing what can still apply is that all the state action pairs in this end component, or this BSCC, must have weight 0. All the cycles must have weight 0. Before I said the criterion is to check the existence of positive cycles, which is equivalent to the existence of negative cycles. And what if this does not apply, then this means that the accumulated weight along all the cycles must be 0. And in that case, what we can do is we can somehow flatten such end components. Now, in the case of non-positive and non-negative weights, I said we simply collapse them to a single state. Here, the situation is a bit more complicated, but if I look at the time, then I think I will skip this. If you like to see it, I'm happy to show it after the talk. Now, so, well, in the end, with this technique to remove end components, we are indeed back to exactly this picture what I've shown you for the case, for Luca Alfaro's case, non-positive or non-negative weights. There is a transformation, which is polynomial time, to a new MDP that satisfies the constraints that are considered by Betzekas and Tsitzlikis, such that we can rely on their machinery and rely on all these techniques that have been developed for the discounted case. So let's look now for variance, and let's start with a few questions. Why do we consider variance? The first thing is, I said here, we consider the maximum over all the proper schedulers. So those schedulers that reach the goal state with probability 1. Is it really justified to ignore the improper ones? And what is the case if there are no proper schedulers at all? If all the schedulers fail the goal state with some positive probability? And another question, just looking for the expectation, then this might not be the best solution. If the maximal, an optimal scheduler is a good expectation, okay, but the variance is very, very high, then there is a very high risk that concrete sample runs have the accumulated weight is much less than the expectation. So in these cases, it might be better to have suboptimal, submaximal expectation, but a better, smaller variance. Looking for the variance, I find it a bit surprising. This is surprisingly difficult. So a natural thing would be to deal with threshold values. I want to have at least this and that expectation, and I have a threshold, an upper bound for the variance. Now, such threshold problems, at least to the best of my knowledge, it is not known to be solvable. What is known is to achieve such thresholds or to satisfy such threshold conditions, one might need schedulers that use both memory and randomization. But I'm not aware that there is any solution method is known. There is a partial answer, but for a much simpler setting, namely if there might be different schedulers that achieve the maximal value. And if you consider only those and you seek for variance minimal scheduler under those that achieve the maximum, then the situation is simpler. More or less, one can use Bellman-like equations for the variance. And what makes it here so simple is, with this question here, the expectation is fixed. It is a fixed value that can be computed before, and then it can be treated as a constant in this linear program. So all the schedulers under consideration here, they have all the same expectation. And it makes it simpler, this problem. So another thing is to look what have people done in risk theory. So there is a notion called variance penalized expectation. So what they do in this context here, where we still want to have a good, high expectation, is to take the supremum over all schedulers that can be achieved for this goal function here. We take the expectation, the expected accumulated weight, minus some factor lambda, some positive value, times the variance. So there is some incentive not only to maximize here the expectation, but also to look for a small variance value. For solution methods for this, I come to this in a second. There is a partial answer. Another measure also taken from risk theory is the so-called conditional value at risk, which has been investigated by Jan Kretinsky and Tobias Meckendorfer. So this value at risk, you fix some probability value or some percentage p, and you are interested what happens in the p worst cases, so in the 10% worst cases. For this, you can define a so-called value of risk here, so where it swaps what are the worst cases, let's say it in that way. And then you look here in this conditional case, what is the expected accumulated weight in exactly these cases, these p worst cases. That's what they do. Solution methods I will talk in a second. So this was already a conditional expectation, but also you can look for this in a clear form, the conditional expected accumulated weight under the assumption that we indeed reach the goal state. This makes it possible to relax this assumption that we only look for the schedulers that achieve the goal with probability 1. Instead, it's sufficient to look for those that reach the goal state at all. And another variant of this one, which is conceptually close to this one, is what has been called partial expectations. So for this random variable, we say take the accumulated weight in case that we indeed reach the goal state, and otherwise 0. Now, these problems look quite different, but they have some similarities. And I will briefly zoom into conditional expected accumulated rewards, and then give you an idea what are the similarities to these other problems. So the first thing, why should we be interested in these conditional expectations? Well, it's a natural measure. For instance, if you have probabilistic non-deterministic programs, then you might be interested in the conditional expectation time under the assumption that the program indeed terminates. Or you might look for certain failure scenarios, and then what are the expected costs of repair protocols in these particular failure scenarios, which gives you your condition. And it has also been used for some kind of multi-objective reasoning or cost utility, to analyze the cost utility trade-off. Let's skip this. It is more difficult than the standard stochastic shortest path problem, because as you will see in a second, optimal memoryless schedulers might not exist anymore. We might need history. And also this using linear programming techniques in this naive form with one variable per state won't work anymore. So let's look at an example, namely this one here. So this is an MDP where it's just a single state where we have a non-deterministic choice, namely S2, where we can go with action alpha directly to the goal state with probability 1. Or we can take action beta with this self loop here, or going to a failed state. So let's look first for the two deterministic schedulers, memoryless deterministic schedulers that always do the same thing when they are in state S. So the first option is always take action alpha in state S2. Then we have just a single path going to, two paths going to goal. One is from S0 via S1 to goal. Then we collect here the reward for this action gamma, which is R. And the other one goes from S0 to S2 and then to goal, and here the reward is 0, so the result is R half. For the scheduler, the memoryless deterministic scheduler, which always chooses beta in state S2, then we indeed achieve a better conditional expectation, namely R. And this is because there is just a single path going to goal via S1. We achieve here the value, the reward, or the weight R for gamma. And the other possibility here for this conditional expectation, we never reach goal, so it's simply ignored. So, so beta is better than alpha. But we can do better. Let's look for the following scheduler. In state S2, for the first n visits, we take beta, and for the n plus first visit, so if we have taken this self loop, if it happens that we have taken this self loop n times, then we take action alpha. So there is still this possibility to going directly from S0 to S1 to goal. This stands for this 1/2 times R. Plus, now 1/2 times the probability to take the self loop n times. This is this value. And whenever we take beta, we earn this weight 1. So altogether, we get here the factor n. Now you can calculate, then the result would be this. And this is better than R. Remind, this was the conditional expectation that we achieve with this memoryless deterministic scheduler, which always chooses beta. So this value is larger than R if and only if this number n is larger than R, and one can compute that the maximum is achieved for n equals R plus 2. Now what this example shows is we can need memory. So in this case, we need a counter for the number how often we have taken this self loop. And what is meant here by saying local reasoning is not sufficient? I just said the optimal value is achieved for this scheduler after R plus 2 visits of S2, we take action alpha. Now this depends on R, which is the weight of this action gamma, which is sitting here. So this transition is even not reachable from S2. Just looking for the sub-MDP that is reachable from S2, we cannot say anything about the optimal behavior in state S2. This is what I mean here with local reasoning is not sufficient. And there is also another phenomenon which does not occur in the unconditional case. For the initial state, the maximal expectation is finite, but, for state S2, if I consider this as the initial state, then indeed this maximal conditional expectation is infinite, because I have here the possibility to pump at infinity and go then to the goal state. So now also in the interest of time, I will just mention the results and skip these details here. If there is a method, so this was on the previous slide, there are graph techniques to check finiteness. So assuming that we have checked this and made sure that the conditional expectation is finite, and assume that all weights are non-negative, so either positive or 0, but no negative values. Then what can be shown is that the threshold problem, so to check whether this maximal conditional expectation is beyond a certain threshold, this is a p-space hard problem and p-space complete in the acyclic case. Now for algorithms in the non-acyclic case, where we have cycles, the key observation is there is what we call a saturation point. So if there is some natural number such that whenever we reached a configuration, a state, and look for the accumulated weight that has been accumulated so far, if this one is larger than the saturation point, then from then on, the best what can do is to maximize the probability of reaching a goal state. And the intuition is that the accumulated weight is already so high such that we want to save, do not want to go the risk that we fail to visit the goal state, in which case we lose everything. That's the intuition behind this. Well, and from this one can derive an exponential time threshold algorithm and an exponential time algorithm to compute this optimal value. Now, this was saturation point algorithm for the case of conditional expectations. And now remember that I mentioned before other variants. The same observation with these saturation points has been made for partial expectation. This is the result by Martha's group. And it has also been made for conditional values for risk. This is the result by Tobias Meckendorfer. And it also applies to the setting of variance penalized expectations. Remind that there the goal was to maximize the objective expectation minus lambda times variance, with lambda being some positive constant. And here is also a saturation point, but here comes some strange phenomenon. Behind that saturation point, the best thing one can do is to minimize the probability to reach the goal state. And the reason is more or less, or intuitively, this variance is a quadratic function. And from some point on, in this objective, the variance becomes the dominant thing. And so what one wants to do is to minimize, from some point on, one wants to avoid that the value gets too high. That's the intuition behind that. Which at the same time makes this variance penalized expectation in this context a bit questionable. And other things that are known are for acyclic MDPs with integer weights. Then it's not a problem because in the acyclic case, we only have finitely many passes. They can be explored using polyspace algorithms. And for many of these problems, I think even for all, a p-space lower bound has been established for this case. So now, so these were restrictions, either non-negative weights or acyclic. Now, what is in the general case, and one indication that this is more difficult, is that these values, the maximal expectation defined in one of these variants, can be an irrational value. So one should not expect linear programming techniques as they are known for the unconditional case. And indeed, and this was the result of Jakob Piribauer in his PhD thesis, what he has shown is that quite a lot of these problems are Skolem or even positivity hard. Now, this Skolem problem is a very prominent and very old problem in mathematics to decide whether a recurrent sequence eventually hits zero or whether all these values are positive. And the decidability status is unknown for quite a long time. Ben, do you know, I forgot when this Skolem problem of positivity has been considered first? Or does anyone? In the? Okay, in the 70s. So also a quite old problem. So, and just a side remark, well, let's say I was surprised to see these results, that these problems are so hard. And Jakob introduced, to my opinion, a very elegant proof technique. So he used the same MDP gadget for encoding linear recurrent sequences to prove the Skolem or positivity hardness for a wide range of problems, also for other problems which have nothing to do with weights, like the model checking problem for frequency LTL in Markov decision processes, or threshold conditions for termination probabilities in one counter MDPs. And these reductions, they only differ in the choice of the initial condition. So let's come to the conclusions. So for the classical stochastic shortest path problem, the key are the Bellman equations, from which we have the this full machinery that can be exploited algorithmically, so linear programming techniques, value iteration, policy iteration. And let's say, there were first these kind of semantic side conditions in the Berzekas Tsitsiki's approach, but after some graph transformations, polynomial time transformations, one can reduce to this case. Now for these variants that I proposed here, or that have been considered in the literature, I found it surprising that they are so difficult in the case of integer weights, this positivity hardness, and quite a few of them enjoy this property that if all the weights are non-negative, then one can exploit the non-monotonicity of the accumulated weights along the prefixes, which gives you a saturation point characterization and then an X-time or X-space algorithm. And one other remark. So this was for Markov decision processes, which are also considered as one-player stochastic games. Now, in the case where you have two players, then let's say the objective of one player is to maximize this expectation and for the other player to minimize. There are some results by Patek and Berzekas from 1999, but at least to the best of my knowledge, this problem has not been completely solved. And there is also this I mentioned this partial expectations. This also in Marta's paper has been considered also in the case of the game setting. But I'm not aware for algorithms for the conditional expectation or the other variants of the stochastic shortest path problem. Now, I almost made it in time. Thank you very much.